Ever looked at a sapphire and wondered, why is it so incredibly blue? Or an emerald? Why is it so green? Well, today, we're diving into the amazing chemical theory that literally paints our world with color. So here's the big question. What is the deal with certain chemical compounds, especially the ones with transition metals? Why do they have these stunning, brilliant colors, while so many others are just, boring white powders or clear liquids? For a long, long time, this was a genuine puzzle for chemists. The old school models, things like valence bond theory, they just couldn't crack the code. They completely failed to explain the colors, and they also couldn't figure out why some of these compounds were magnetic and others weren't. To solve this, we needed a totally new way of looking at the problem. A different kind of model that just shifted the focus a little bit and suddenly made everything make sense. And that model is called crystal field theory. Now, the big idea behind crystal field theory, or CFT, is actually kind of simple, which is what's so brilliant about it. It basically ignores all the complicated stuff about chemical bonds and just zeroes in on one thing: electrostatic forces. It just treats the metal in the middle and the molecules around it, we call those ligands, as little points of charge that are all pushing away from each other. That's it. It's all about repulsion. And right here, this is the breakthrough. Instead of getting bogged down in how electrons are shared, CFT just said, hey, let's just look at how these things repel each other. And with that one simple change in perspective, it suddenly explained both mysteries, the color and the magnetism. Just like that. So, how in the world does simple repulsion lead to these amazing effects? Well, it all comes down to how those surrounding ligands mess with the electron orbitals of that metal atom in the center, specifically something called the d orbitals. Okay, let's walk through this, because this is the core mechanism. First, picture a metal ion just floating by itself. All 5 of its d orbitals have the exact same energy level. But then, as you see in step 2, 6 of these ligands come in and surround it, approaching right along the x, y, and z axes. Now, this creates that repulsion we talked about. And here's the key part in step 3. The orbitals that are pointing directly at those incoming ligands get a huge push, energetically speaking. They get shoved up to a higher energy. The orbitals pointing in between the ligands, they don't feel it as much. And the result? Bam. Step 4. You get a split. The d orbitals are now at 2 different energy levels. And that energy gap right there, the space between those 2 new levels, has a name. It's called the crystal field splitting, or for short, delta oct. And I'm telling you, this one value, the size of that gap, is the absolute key. It's going to unlock everything for us. So let's move on and see exactly how this energy gap explains the whole magnetism mystery. All right, so here's where it gets interesting. When you start adding electrons into these new split orbitals, the electrons have a choice to make, and that choice comes down to a competition. Is it easier to jump across that energy gap to an empty orbital upstairs? Or is it easier to just pair up with another electron in a lower orbital, even though electrons hate being paired up? It all depends on the size of that gap. Let's start with what we call weak field ligands. These guys, they only cause a little split, a really small delta oct. So for an electron, that tiny energy gap is like a small step. It's way easier to just take that small step up to an empty orbital than it is to force itself into an already occupied orbital downstairs. A perfect example is this iron complex with water. Water is a weak field ligand, so that gap is tiny. You can see how the electrons choose to spread out, one in each orbital, before they even think about pairing up. The result is you have a bunch of unpaired electrons, and that makes the whole compound paramagnetic, which just means it's attracted to a magnet. But what happens if we use strong field ligands? Well, these cause a massive energy split, a huge delta oct. Now that energy gap isn't a small step anymore, it's a giant leap. And it's actually easier for an electron to just hold its nose and pair up in a lower orbital than to make that huge jump. So let's swap out the water for cyanide. Cyanide is a super strong field ligand, creating this massive energy gap. Now look what the electrons do. They fill up all the lower orbitals completely before even considering that big jump. This means you end up with 0 unpaired electrons. And that makes the compound diamagnetic. It's actually slightly repelled by magnetic fields. So mystery number 1, magnetism, is solved. Now for the grand finale. Connecting that exact same energy gap, delta oct, to those gorgeous colors we started with. The idea here is actually pretty elegant. Light is energy, right? So an electron that's chilling in one of those lower d orbitals can absorb a photon of light, but only if that photon has the perfect amount of energy needed to jump across the delta oct gap and land in a higher d orbital. So get this, white light from the sun has all the colors of the rainbow in it. When that light hits our compound, the compound basically eats the one specific color of light that matches its energy gap. So what do our eyes see? We see all the other colors that were not eaten, the light that's left over. We see the complementary color. Take this copper complex, for example. It looks bright blue to us. Why? Because the molecule is literally absorbing the orange and red parts of the light spectrum. When you take orange and red out of white light, what's left behind for your eye to see? Yep, blue and green. And this brings us right back to our ligands. Weak field ligands make a small gap, so they absorb low energy light, like red. And if you absorb red, you look blue-green. Strong field ligands make a huge gap, so they absorb high energy light, like violet. And if you absorb violet, you appear yellow. This table just ties it all together beautifully. Look at our two iron compounds again. With the weak water ligand, it absorbs low-energy red light and looks blue-green. Swap in the strong cyanide ligand, and it absorbs high-energy violet light and looks pale yellow. It's the same metal, just changing the ligand gives it a completely different color. How cool is that? Okay, this brings up one last obvious question. If this is all true, then why are some of these transition metal compounds just white? Why are they colorless? And the answer is actually really simple. There's no room at the in. For an electron to jump, there has to be an empty spot for it to land in. But if a compound has what we call a d10 configuration, it means all 10 spots in the d orbitals are already full. It's a sold-out show. So no jump is possible with visible light, which means no color is absorbed. And if no color is absorbed, the compound just looks white. So let's just pull this all together. It all boils down to one simple, powerful idea. Those surrounding ligands split the energy of the d orbitals. That energy gap, that delta oct, is the master key. The size of that gap tells the electrons how to arrange themselves, which explains the magnetism, and that exact same gap tells the compound which specific color of light to absorb, which explains its brilliant color. And that leaves us with a really fascinating thought to end on. If we understand this system so well that we can predict a compound's color just by knowing its ligands, could we do it in reverse? Could we become molecular artists, designing molecules with specific ligands to give us any custom color we can imagine? Think about the possibilities for everything from new kinds of dyes to futuristic electronic displays.